Welcome back, fellow philosophy fans. Today, we're taking a deep dive into something that might seem a bit, well, unexpected for us. The history of computing.
It might not sound like our usual philosophical territory, but trust me, there are some really fascinating links between how machines have evolved and, well, how we think about the mind.
Yeah, when I first saw the reading list for this one, I have to admit, I thought, uh-oh, this is going to be a bit technical. But
Right.
but then as I started digging in, I realized that the history of computing, it's full of these aha moments.
Oh, absolutely. And to really appreciate those aha moments, we need to understand where it all started.
Okay, so where do we begin?
Believe it or not, with people.
People. Wait, you mean like ancient philosophers sitting around, like
Right.
contemplating algorithms?
Not quite. I'm talking about human computers. These were individuals, often women, who basically were the calculating machines of their time. They did incredibly complex calculations all by hand.
Wow. So before we had machines crunching numbers, we had these brilliant minds doing all the heavy lifting.
Exactly. And it's in this context that the work of someone like Charles Babbage becomes even more remarkable.
Babbage. Now, I vaguely remember him from like philosophy of technology readings, but remind me.
He was a 19th century mathematician who dared to imagine machines that could automate that really demanding intellectual labor that the human computers were doing.
So like the OG computer visionary, right?
Yeah.
What were these machines he was dreaming up?
Well, he actually envisioned two revolutionary machines. The first was the difference engine. It was designed to automatically produce those mathematical tables that human computers spent countless hours creating. Those tables of logarithms and trigonometric functions.
Right. But did he actually build it?
He built a small working model but never finished a full-scale version. But here's the mind-blowing part. In 1990, a team of engineers, they actually built a working model of the difference engine.
Wait, they used Babbage's original designs.
Yeah. And guess what? It worked flawlessly.
Wow. That's incredible.
It really is. And speaking of incredible, Babbage's second machine, the analytical engine, was even more ambitious.
Okay, so what was that?
Well, think of it as the great-great-grandfather of the computers we use today. It was a design for a general-purpose computer.
A general-purpose computer back in the 19th century. What did that even mean?
It meant a machine that could theoretically compute anything computable. Babbage imagined this machine with a memory store, a central processing unit, what we call a CPU today, and even the ability for the machine to make decisions based on its previous calculations. We call this conditional branching now.
Wow, so he was not just automating calculation. He was essentially laying the foundation for a machine that could, like, process information, make decisions, almost like you could think.
Precisely.
This was all before electricity was even widely used. It's mind-boggling. But how would they even control such a complex machine?
Well, Babbage borrowed a brilliant idea from the Jacquard loom. The one that used punched cards to create those intricate woven patterns?
Right.
So he proposed using similar punched cards to program the analytical engine, feeding it both data and instructions.
Punched cards, huh? Those things they used to use for computer programming way back when.
Exactly.
It's amazing to think that something so seemingly simple could hold the instructions for such a sophisticated machine.
Absolutely. And it was the recognition of this very power that captivated the imagination of Ada Lovelace.
Ada Lovelace. Now, she was a fascinating figure. Tell me more about her role in all of this.
She was a brilliant mathematician and a close collaborator with Babbage. Lovelace not only understood how the analytical engine worked, but she also saw its potential beyond just crunching numbers. She even suggested it could someday compose music.
Wow, composing music with a machine. That's incredible. She's clearly way ahead of her time.
Absolutely. Her insights really foreshadow the amazing range of things that computers can do today. Everything from creating art to simulating entire universes.
So we've got these mechanical marvels being dreamed up. But the world of computing was about to take a pretty dramatic turn, right? Enter analog computation.
You got it. While Babbage was focused on digital representation using numbers, another approach was gaining traction: analog computing. This used physical quantities like length, voltage, or even water pressure to represent and manipulate data.
So instead of ones and zeros, an analog computer might use, say, the angle of a wheel to represent a number.
Precisely. Think of a slide rule where the length of a segment represents a specific value. or an acoustic depth meter, where the pitch of the sound represents the depth of water. These are all examples of analog representation.
So it's like the digital world is all about abstract symbols, while the analog world is trying to create these physical analogs for the information being processed.
Exactly. And there were some pretty sophisticated analog computers being built. Take James Thomson's wheel and disc integrator. It could solve really complex mathematical equations using a system of rotating wheels and discs.
Oh, and wasn't his brother, Lord Kelvin, the one who used that technology to build a tide-predicting machine?
That's right. And then there's Vannevar Bush's differential analyzer, built in 1931. It was the first large-scale automatic general-purpose analog computer. It was a groundbreaking achievement.
So analog computing was a serious contender in the early days. What led to its decline?
Well, analog computers had a major limitation: precision. As problems got more complex, it became really hard to achieve the accuracy needed for reliable results. Digital systems, with their ones and zeros, could achieve far greater precision.
So the digital world, with its ones and zeros, ultimately proved to be more precise and scalable. But to really understand this digital revolution, we need to talk about one of the most influential figures in the field, Alan Turing.
Absolutely. In 1936, he published this groundbreaking paper that laid the theoretical foundation for the modern computer. It described the universal Turing machine.
Okay, for our philosopher friends out there, break this down for us. What exactly is a universal Turing machine?
Well, imagine a simple machine. It has unlimited memory. It has a scanner that can read and write symbols, and it has a program of instructions. Crucially, this machine can modify its own program as it runs. Essentially, it's a universal toolbox for computation.
Okay, so it's not about gears and levers. It's a theoretical model for how a machine could process information and solve problems. But how did Turing connect this abstract model to real-world computing machines?
He was fascinated by artificial intelligence. He used chess as an example, exploring how a machine could learn from experience and use what we call heuristics, or rules of thumb, to solve problems.
So even back then, he was thinking about machines that could potentially think, learn, and strategize. That's an idea with some serious philosophical implications. But let's not get ahead of ourselves. These early computers were still largely electromechanical, right? Lots of clunky, slow relays.
Right. To achieve the speed and power that Turing envisioned, a different technology was needed: electronics.
Enter the vacuum tube.
Exactly. Vacuum tubes could switch electronic signals on and off incredibly fast and with no moving parts. It was a game changer for computing.
So who was the pioneer in using vacuum tubes for large-scale computing?
That would be Thomas Flowers, an engineer working for the British Post Office. In the 1930s, he was designing telephone exchange equipment using thousands of vacuum tubes.
Okay.
And this experience gave him the idea that vacuum tubes could be used for high-speed digital computation.
And that led to Colossus, right?
Yes, Colossus was the world's first fully functioning electronic digital computer, built in secret during World War II to break German codes.
It sounds like something straight out of a spy novel.
It was top secret. It processed data at speeds unimaginable just a few years earlier.
So Colossus used thousands of vacuum tubes to crack Nazi codes. It was a giant leap forward, but unlike Turing's universal Turing machine, Colossus wasn't a stored programmed computer. They had to rewire it for each new task, right?
That's right. But its success really showed the potential of large-scale electronic computing and paved the way for the development of truly general-purpose, stored program machines. Machines that could be programmed to do a whole variety of tasks.
And that's where we'll pick up in the next part of our deep dive, the race to build the first stored program computer.
It's a fascinating story, full of brilliant minds and some surprising twists and turns.
Stay tuned, folks. The story of computing is about to get even more exciting.
And the philosophical implications even more profound. Welcome back to our deep dive into the history of computing. As we saw in Part 1, Colossus proved that large-scale electronic computation, it was possible. But the race was on to build a machine that could not only crunch numbers super fast, but also store and modify its own instructions, a true thinking machine, well, at least in a very early form.
Yeah, the stored program computer, a concept that would really revolutionize computing. And it seems like there were several brilliant minds all working on this at the same time.
Right. The development of the stored program computer, it happened almost simultaneously on both sides of the Atlantic. Researchers were building on each other's ideas, pushing the boundaries of what was possible. It was a really exciting time.
It sounds like a thrilling chapter in our computing saga. So where do we begin this part of the story?
Let's start with John Atanasoff, an American physicist and mathematician. Back in the late 1930s, he wanted to build a small-scale electronic computer just for solving systems of linear equations.
Okay.
It was a problem that he kept running into in his physics research.
Right.
So with his graduate student, Clifford Berry, he built what they called the Atanasoff-Berry computer, or ABC for short.
So the ABC was designed for a specific mathematical task, not quite the general-purpose computer we have today.
That's right. It was purpose-built. However, it was still a major step forward. It showed that you could use vacuum tubes for digital calculations, and this paved the way for more versatile machines.
And it's fascinating that this was happening around the same time that Colossus was being developed in secrecy over in Britain,
Right. Innovation, it often happens in multiple places at the same time.
driven by different needs and motivations.
Exactly. And while the ABC was a big development, it was Alan Turing who really laid out the blueprint for the modern stored program computer with his concept of the universal Turing machine.
Ah, Turing, back again.
Uh,
We talked about his theoretical work in part 1, but how did he actually contribute to building a real computing machine?
After the war, after his code-breaking work, Turing joined the National Physical Laboratory in London to design and build a general-purpose electronic computer. He called it the Automatic Computing Engine, or ACE.
ACE, huh? Another nod to Babbage's analytical engine.
Yeah.
I love it. And wasn't Turing known for thinking, way outside the box?
Right.
What was his vision for the ACE?
In 1945, he wrote this super detailed report outlining the AC's design. It included circuit diagrams, hardware specs, even sample programs written in machine code. It was like he had the entire blueprint in his mind.
Wow, so he wasn't just a theorist, he was thinking about the nitty-gritty details of actually building this thing.
Exactly. And speed and memory capacity, those are really important in his design.
Well, those are still key factors in computers today.
Right. He knew that to really tackle complex problems, a computer would need to process information fast and store huge amounts of data. He even proposed a high-speed memory comparable in size to early Macintosh computers.
So he was envisioning a machine that could hold, gigabytes of data? That's insane for the time. But did they ever actually build Turing's ACE?
Well, building the full-scale ACE was really difficult. There were a lot of bureaucratic problems at the National Physical Laboratory, but a smaller pilot model of the ACE was built, and it successfully ran its first program in 1950.
So a scaled-down version of Turing's dream machine came to life.
Yeah.
That's still an amazing achievement.
Yeah, the pilot ACE, it was a marvel. It ran at 1 megahertz,
Okay.
which made it the fastest computer in the world at that time.
So speed seems to have been a constant theme in early computer development, this drive to make these machines faster and faster.
Yeah, you can see that happening on both sides of the Atlantic. While Turing was working on the ACE in Britain, a group of pioneers in the US was also trying to build a stored program computer.
Okay, so let's hop across the pond. Who were the American trailblazers?
Well, we talked about John von Neumann in the last episode. He was a brilliant mathematician and played a key role in developing ENIAC, the first fully functioning electronic digital computer in the US.
Ah, yes. ENIAC, that giant machine with all the flashing lights. It really captured the public's imagination. But wasn't ENIAC more of a specialized calculator than a true programmable computer?
That's right. But its development led to a proposal for a new machine called EDVAC, and this new machine would explicitly store program instructions in its memory alongside the data being processed. It was a fundamental shift in how people thought about computers.
So EDVAC was like the American counterpart to Turing's ACE. But I thought Turing's Universal Turing Machine, which was published years earlier, already had the stored program concept.
You're right. Turing deserves full credit for that. However, it seems that other brilliant minds, people like von Neumann and Presper Eckert, one of the ENIAC's creators, they independently came up with the idea of a stored program computer. It's kind of amazing how great minds often converge on the same solutions, even when working totally separately.
It really makes you think about the nature of discovery, doesn't it? So we've got Turing in Britain, von Neumann in the U.S., both working on this stored program idea. But who actually built the first working stored program computer?
Well, there's another important person in this story, Max Newman. He was Turing's mentor at Cambridge, and he was instrumental in establishing the Computing Machine Laboratory at Manchester University.
Manchester University, that's where they built the
Manchester Baby.
Manchester Baby, right?
It was the world's first working stored program computer. It successfully ran its first program on June 21st, 1948. It was a truly pivotal moment.
Wow, so the first stored program computer was born in Manchester, and it all happened so quickly. Who were the masterminds behind it?
It was a team effort. with brilliant engineers like Freddie Williams and Tom Kilburn, who designed and built the machine, and of course Max Newman, who, provided the theoretical foundation, drawing heavily from Turing's work.
So Turing's ideas were really having an impact, not just at the National Physical Laboratory, but also at
Right.
Manchester. It's incredible how influential his work was. What happened to the Manchester baby? Did it end up in a museum somewhere?
Well, sort of. It paved the way for the Ferranti Mark I, which was the world's first commercially available computer. It was installed at Manchester University in 1951. So in just a few years, we went from this small experimental machine in a lab to a computer you could actually buy.
That's amazing. The pace of progress was incredible.
Yeah.
But as these early computers became more sophisticated, didn't they run into some problems with memory? Being able to store and quickly access information.
You're absolutely right. Memory, it was and still is super important for computer performance. And as computers got more powerful, they needed better and more efficient memory systems. This led to a lot of experimentation with different memory technologies.
So it wasn't just about building faster processors, it was also about finding better ways to store and retrieve information. What were some of the memory technologies they were experimenting with?
One of the first forms of high-speed memory was the mercury delay line. They stored data as sound pulses traveling through tubes filled with mercury.
Mercury delay lines, that sounds complicated. Why mercury?
It was a pretty clever idea. Imagine a tube filled with mercury, with a special crystal at each end. When you send an electrical pulse representing a bit of data into the tube, it creates a sound wave that travels through the mercury.
So the data is literally sound waves in a pool of mercury.
Hmm.
Amazing. How do you get the data back out?
At the other end, the sound wave hits another crystal, and that converts it back to an electrical signal, which can then be read.
It's like a computer program as a sound wave.
Mm.
It makes you think about the nature of information.
Yeah. But mercury delay lines, they had a problem. They were sequential. To access a specific piece of data, you had to wait for it to travel down the tube.
Oh, so it wasn't like the random access memory we have today.
Right. But Turing came up with a clever solution. He called it optimum coding. He basically arranged instructions in the delay line so that each instruction would be ready right when it was needed.
So Turing was optimizing the instructions to work with the limitations of the hardware. Pretty ingenious.
It was. And it helped them get more performance out of those mercury delay lines, but it also made programming a lot harder.
A trade-off.
Yeah.
But while they were working on that, weren't other people exploring different memory technologies that were faster and had more capacity?
Yeah. And one of the most promising ones was the Williams tube, or electrostatic memory. It was developed by Freddie Williams, one of the pioneers of the Manchester baby.
Okay.
It used a cathode ray tube, like the ones in old TVs, to store data as charge spots on the screen.
A TV screen as a memory bank. That's really creative. What were the advantages of using that?
It offered random access. You could access any data directly. You didn't have to wait for it to cycle through, like with the mercury delay line.
So that was a big step towards the kind of instant access memory we have today. What about other memory technologies from that era? Wasn't there something called drum memory?
Yeah, drum memory was another popular technology. It used a rotating metal cylinder coated with a magnetic material to store data, like a really early hard drive.
Interesting. So the data was magnetically encoded on a spinning drum. What were the advantages of using that?
It was a good balance between speed and capacity, and it was more reliable than mercury delay lines, which were really sensitive to temperature changes and vibrations.
Makes sense. But I have a feeling that the biggest breakthrough in computer memory was still to come.
Right.
Magnetic core memory.
You got it. It was a technology that dominated computing for a long time.
I remember my computer science professor going on and on about those tiny magnetic rings.
They were pretty cool. They used these little rings called cores made of magnetic material.
Cores, like little magnetic donuts.
Exactly. Each core could be magnetized in one of two directions, representing a 0 or a 1, and these cores were arranged in a grid, creating a 3D matrix of memory cells.
A grid of tiny magnetic donuts holding all the information.
Huh?
Wow. But what was so great about magnetic core memory?
It was fast, it was really reliable, the data stayed even when the power was turned off. It was relatively cheap to make, and it was non-volatile, meaning that the data was stored permanently even when the power was off. This was a big improvement over earlier systems where you would lose the data if the power went out.
So magnetic core memory was the whole package. Fast, reliable, affordable, and it kept the data safe. No wonder it became so popular. And it helped to make computers even more powerful and versatile, right?
Absolutely. And in the final part of our deep dive, we'll see how this memory revolution, along with Other advancements in hardware and software led to the computers we have today. From those early specialized machines to the devices we rely on now, it's a change that has some pretty deep philosophical implications, raising questions about intelligence, the limits of computation, and even the future of humanity.
Can't wait to hear more about that. But for now, let's take a minute to appreciate the amazing journey we've been on. From human computers to the incredible inventions of Babbage, Turing, and all these other pioneers.
It's been quite a journey, tracing the roots of modern computing. And in the next episode, we'll see how these innovations laid the foundation for the digital age and explore how computers have changed the world and how we understand ourselves.
Welcome back to the Deep Dive. In the last two parts, we journeyed from human computers to the birth of the stored program computer, the memory revolution, all that.
Right.
Now we're in the final chapter, and things are about to get, well, even more interesting.
Indeed. We'll see how those early innovations set the stage for a technological revolution that's changed the world in ways that are both amazing and, well, a little unsettling.
Okay, so last time we were talking about magnetic core memory, those
Mhm.
tiny magnetic rings.
Mm.
But memory is just one part of the story. What else drove computing forward?
Well, one of the biggest things was the invention of the transistor.
Ah, yes, the transistor. Hard to imagine the world without them.
Right.
They're everywhere, but remind me what made them such a game changer.
Well, transistors were smaller, faster, more reliable, and they used a lot less power than vacuum tubes. So you could pack more computing power into a much smaller space, which meant computers could get smaller and cheaper.
So it wasn't just a tech thing, it actually changed who could use computers, who could afford them.
Exactly. And that trend towards miniaturization continued and led to the development of integrated circuits, or ICs.
Right, ICs, combining multiple transistors onto a single tiny chip.
Exactly. All that circuitry squeezed onto a chip. It was remarkable. And that led to this huge growth in computing power. Moore's law.
Ah, yes, Moore's law. The number of transistors on a chip doubles roughly every 2 years. It's pretty incredible how accurate that's been.
It really is. And this constant doubling of computing power, well, it's driven costs down and made computers more capable. It's had a huge impact on how we think about technology and its effect on society.
It's like an unstoppable force. This constant push for more power in smaller packages makes you wonder where it all leads. But let's get back to the history for a bit. So transistors and integrated circuits, they made computers smaller, cheaper, faster. What happened next?
One thing that happened was the development of mini computers. Smaller, less expensive computers that companies and organizations could use, ones that couldn't afford those big mainframes.
So computing wasn't just for big corporations anymore. It was becoming more accessible.
Right, and that continued, which led to the development of microprocessors in the early 1970s.
The microprocessor, the brain of a modern computer. Tell me about that.
A microprocessor is basically a CPU, a central processing unit, but all on a single chip. So all the circuitry needed to run programs, it was all squeezed onto this tiny piece of silicon.
Wow. And that's what made personal computers possible, right?
Exactly. The microprocessor really paved the way for the personal computer revolution.
Ah, the PC. Those beige boxes that started popping up everywhere. Apple, Commodore, IBM, all those names.
Yeah. The PC changed how we work, how we learn, how we communicate. It gave people access to computing power that, used to be only for big institutions.
It was a huge shift. Anyone could own a computer, write a program, create things. But I remember those early PCs being kind of hard to use. Lots of complicated commands and weird text interfaces. What changed that?
Well, graphical user interfaces, GUIs, were a big part of it.
GUIs, with their windows, icons, menus,
Yep.
made computers much easier to use.
Right. You didn't need a computer science degree to use a computer anymore. GUIs and cheaper PCs, those led to a huge increase in software, too. Word processing, spreadsheets, games, all sorts of things.
Yeah, it's hard to imagine life without those now.
Mm.
But it was the internet that really made personal computing take off, wasn't it?
Absolutely. The internet, a global network of computers, it revolutionized communication, how we do business, how we share information. It created new ways to work together, to innovate, to be social, connecting people across the world.
The internet. Hard to overstate its impact, right?
Definitely.
But like any powerful technology, it comes with its own set of problems, right?
Of course. Privacy, security, misinformation. And there are new forms of social isolation and addiction, too. It's a powerful tool, and we have to learn to use it responsibly.
So we've unlocked this amazing power, but we're still figuring out how to use it for good and avoid the bad. A challenge for the 21st century, for sure.
It is.
But as we wrap up our deep dive, I'm just amazed by the ingenuity and creativity that's driven this technological revolution.
It is incredible, isn't it? From human computers to a global network of computers, the journey of computing really shows what the human mind can do.
And as we've seen, it raises some really big philosophical questions. It makes us rethink how we understand intelligence, consciousness, and even reality itself.
It really does. The history of computing, it's not just about machines. It's about us trying to understand ourselves, to create tools that help us do more, and to see what's possible.
So as we finish up, I have to ask, what's next? What new things will we discover? What new challenges will we face? What does the future hold for computing and its impact on humanity?
Big questions. We're still in the early days of this incredible story.
And who knows, maybe some of you listening will be the ones writing the next chapter, pushing the boundaries, shaping the future of computing in ways we can't even imagine. It's a future with a lot of potential, both good and bad, but it's a future shaped by the power of computing.
Thank you for joining us on this journey through the history of computing. We hope you found it interesting and that it made you think about these big questions.
And until next time, keep exploring, keep asking questions, and keep wondering. The future of computing, and maybe even the future of humanity, is in your hands.